we have been discussing about the Woodward-Hoffmann rule, and we have so far discussed about, or we have so far derived or drawn the uh, orbital correlation diagram for dimerization of olefin leading to the formation of cyclobutane, and we have seen how we can find out that this reaction, that is the dimerization of olefin, is thermally forbidden just by looking at the orbital correlation diagram. So we will extend this particular discussion further during this lecture, and what we will see is that the electronic configuration that we obtain from this orbital description is not enough to describe the electronic structure of the molecules, and we should explicitly look at instead the electronic states that arise from these electronic configurations, and then uh, we can uh, we can understand the Woodward-Hoffmann rule in more detail. Now, the electronic states or the symmetry of the electronic states can be easily derived by doing just direct product representation of the occupied orbitals, and that is the case for singly degenerate states essentially, because for degenerate states you will, and the direct product will give you essentially a reducible representation, not an irreducible representation. And at least for single degenerate states, we can find out the symmetry of the states by doing simply the direct product of the orbitals. So let us write the electronic configuration of the reacting system, or electronic configuration of states which are of interest to us in the reacting system, that is two ethylene molecules, and also in the product, that is the cyclobutane. Now, in order to write the electronic configuration, what we will do is that we will use a different sort of notation to write the electronic configuration. So, if there are, say, two electrons in an orbital with A2 symmetry, then we write the configuration as A1, 2, just to denote that there are two electrons in an orbital of symmetry A1. So now let us write the electronic configuration of the ground electronic state of the reacting system, and then derive the symmetry of this particular electronic state. So the ground electronic configuration of the to reacting system is A1 2 B2 2. So as we see, there are two electrons in an orbital with A1 symmetry, and there are two electrons in an orbital with B2 symmetry. So now to find out the symmetry of the electronic state or ground electronic state over here, what we will do is that we will take the direct product of the orbitals here, because there are two electrons in A1 orbital of A1 symmetry. So we do direct product of A1 with A1, and then we go ahead and then do direct product of B2 with B2. So this direct product will give us the symmetry of the electronic state of this particular electronic configuration. So the answer is going to be equal to A1. So the ground electronic state of the reacting system has A1 symmetry. So we can again write it over here that the ground electronic state, uh, that is A1 to B22 electronic configuration, it has a symmetry of A1 in case of the uh, reacting system. Now let us write the first excited state of the reacting system. The first excited state we obtained by lifting an electron from this B2 orbital to this B1 orbital. So the electronic configuration is going to be A1 to B2 1 B1 1. So if we find out the symmetry of this electronic configuration, that is A1 cross A1 cross B2 cross B1. So the answer to this particular direct product is going to be equal to B2 into B1 is going to be equal to A2 essentially, because A1 into A1 is going to be A1, B2 into B1 will be equal to A2, and A1 with A2 will again give us answer A2. So this direct product is going to be equal to A2. So this the first excited state of the reacting system with the configuration A1 2, B2 1, and B1 1. It has A2 symmetry. Then we also now have to write the electronic configuration in the reacting system, which is an excited state electronic configuration of the reacting system, which is essentially the ground electronic state uh, of the, or which correlate with the ground electronic state of the product over here. So we see that the product electronic configuration, the ground electronic configuration is A1 to B1 2, and so we write that electronic configuration A1 to B1 2 in case of the reacting system, and that is going to be an excited state electronic configuration in case of the reacting system, and the symmetry of this excited state electronic configuration, if you can find out again, is going to be equal to A1 over here. And then we will write now the electronic configuration or the symmetry of the electronic states for the product. So as we see that the ground electronic state of the product is equal to A1 2, B1 2, and we have already found out that its symmetry is equal to A1. Now we write the energy of the, because if we assume this to be the energy scale, then the energy of the ground electronic state in case of the product is lower than the energy of the ground electronic state of the reactant, as because there is stabilization during the reaction, and that is why we write the energy of the ground state at lower energy than the energy of the uh, for the product than the energy of the ground electronic state in the reacting system. So then in the first excited electronic state in case of the product is when we obtain it by lifting an electron from the B1 to B2 orbital over here. So then the configuration is A1 2, B1 1, B2 1. That is the configuration, and again in this case as well, the symmetry that we are going to get by doing direct product of the orbital or symmetry of the orbitals, occupied orbitals, we will get this to be equal to A2, and then the energy, we will write now an excited electronic state in the product, but this excited electronic state has to correlate with the ground electronic state of the reactants, and we know that the ground electronic state in the reactant is B22 over here, and this state also the symmetry is equal to A1. So that is an excited electronic state in the product. So let us now correlate the electronic states of same configuration and same symmetry in case of the reactant and then in case of the product, and then we will get an electronic state correlation diagram unlike the orbital correlation diagram that we have drawn earlier for this dimerization of ethylene reaction. So when we do so, what we see that this excited state in the product correlate with the ground electronic state of the reactant here, and that is again in case of the the ground electronic state in the product correlate with this electronic state, excited electronic state in the reactant, and then this particular electronic state, that is the A2 electronic state, the first excited state in the product, and and the reacting system essentially correlate with each other. Now there is a law which does not allow us to correlate orbitals of same symmetry by doing this sort of crossover. So this law we call the non-crossover law, and this is essentially there because of electronic repulsion. So that is why this electronic state of A1 symmetry we cannot correlate with this particular electronic state because it has to cross another state of A1 symmetry over here. So the electronic state, this sort of crossover is not allowed quantum chemically, and that is why this crossover cannot take place. So we cannot correlate this particular ground electronic state with the excited electronic state of same symmetry in case of the product here. And instead of that, what we'll have to do is that we have to correlate the this excited state in the reactant with the excited state in the product, and the excited state, ground electronic state of the reactant with the ground electronic state in the product in this particular fashion. And this essentially tells us that the reaction cannot now proceed from the ground electronic state, because the correlation of orbitals of same symmetry is not possible in this particular case. And instead of the ground electronic state, the reaction can take place in the first excited electronic state. The reaction can directly correlate the orbital of the same or electronic state of the same symmetry in the reacting system now correlate with an electronic state of the product with the same symmetry, and that is why the dimerization of olefin cannot take place in the ground state, and that is why we cannot do it, or it is forbidden thermally, but it can proceed in the when the reactants are in excited state, and that is possible, or the reaction is that is why feasible when we perform the reaction photochemically, because when you do photochemical irradiation, essentially you excite the you take the molecule to an excited state, or the first excited state over here, and then it can now go to the first excited state of the product, and that is how the cyclobutane molecule can form from these two ethylene molecules photochemically. And this is essentially the reason why the dimerization reaction of ethylene is thermally forbidden, but it is a photochemically allowed reaction. So this electronic state correlation diagram explains, or is in a way complements the orbital correlation diagram, or the information that we gathered from uh, the orbital correlation diagram, and enhances our understanding of this uh, symmetry selection rule in this pericyclic reaction. So this essentially brings us to the end of this lecture. What we have learned during the last lecture as well as in this lecture is how one can use symmetry considerations to understand the feasibility of a particular reaction, and we have explored this by using this Woodward-Hoffmann law, and we have used, or we have tried to understand the how one can arrive at these selection rules by taking the example of the dimerization olefin as the reaction here, and we have discussed how we can correlate the orbitals of the same symmetry in the reacting system with orbitals of same symmetry in the product, and how one can draw an orbital correlation diagram, which essentially tells us that the 2 plus 2 cycloaddition reaction here is not thermally feasible. When we extended this by using electronic states, or correlating the electronic states in the reacting system with the electronic states in the product, we saw that the 2 plus 2 cycloaddition reaction essentially cannot proceed, or is proceed in the ground electronic state because of this non-crossover law over here, and that is the reason now we could also understand that uh, the reaction is feasible in if the reacting system is in first excited state, and that essentially gives the cyclobutane molecule again form the cyclobutane molecule in the first excited state, because the first excited state in the reacting system correlate with the first excited state in the product, and this is essentially the reason why the 2 plus 2 cycloaddition reaction, or the dimerization of olefin, is photochemically allowed reaction. So let me conclude this lecture with this. We will continue our discussion on Woodward-Hoffmann law, and we will discuss about 4 plus 2 cycloaddition reaction in the next lecture. So I look forward to see you in the next lecture. And I thank you very much for being with me during this lecture. Thank you very much.